Hello everyone, my name is Ruben de Dekker. I am a PhD student at the Knowledge on Web Scale research group at Ghent University. This video is for my presentation for the ICWE 2021 conference, and I come to present you our latest work, which is a file-based linked data fragments approach to prefix search. So why do we need prefix search? Well, a lot of applications and web pages on the web, they make use of data sets that contain hundreds and thousands of data entities. For example, this web application in the picture here is a web application for the public transport stops here in Flanders. And this one has a lot of different transport stops, but of course the user does not need to know every transport stops. The user is only interested in a few specific entities of the data set, which are their start and their stopping transport stop. So how can we provide the user with the possibility to retrieve these specific entities from these data sets? Well, then we provide functionality such as prefix search over the entities of the data set. But how can we provide this prefix search functionality? Well, a first solution is to use a server API. So on your server you are going to start up a program that indexes the dataset that you have and exposes this dataset over an API specific to this program. Clients can then query this interface with a query string with a prefix. The server will look in the dataset index where there are matching entities for this prefix and will return these results to the client. There are already open source toolings available for this. An example is Elasticsearch. Is a very powerful tool to provide such and much more functionality. But these tools often also come at a cost. They have a setup cost. It's not always easy to set up these tools. They have a maintenance cost. As the server is responsible for answering all the client queries, there is need for an active server environment, so the application has to run somewhere. So you cannot make use, for example, of static file hosting such as on GitHub Pages. And this also has a lasting maintenance cost for as long as you want to hold up this API. As long as you want to keep it online, you will need to have the server available for this program. And requests can also be expensive and require throttling on the side of the client and the server to not swamp the server with requests. Another option is to rely on third parties and say we present our dataset as is, we publish it to the web. You can publish it on solutions like GitHub Pages, and you rely on the clients themselves or the third parties to reuse the data, provide their own APIs and do their own lookups in these datasets. And now these are of course less attractive to work with, because every time there's a new dataset you have to re-download it and process again to again set up your API index, or for a client you have to re-download the whole dataset to locally process the data. So this does not this is not an interesting solution for reusers or for clients to use your dataset. So this will not be very popular dataset to use in applications. And application developers will look for other datasets that are more available. So what can we do about this? Well, instead of just publishing our dataset as is, we can provide a specific fragmentation of our dataset. As in this example, the publisher does not only provide the dataset, he provides specific fragments with, for example, the entities of Alice to Bob, the entities of Brian to Dennis, and the client or a third party that wants to access specific, wants to find specific entities in this dataset. For example, if you look for Carol in this dataset, you can easily find the fragment where this data is located, and you only have to retrieve a very small section of the entire data of the dataset instead of having to retrieve the entire dataset. So concretely, what is our proposal? We propose a file-based architecture that allows us to do prefix search with an acceptable user-perceived performance, and that enables clients to take control of the query evaluation. Now that's a long sentence, so we're going to analyze it. So the first part is that we provide a file-based architecture. So just like you would publish your dataset as a big file on the web, you can publish your fragmented dataset as a set of smaller files and just publish these files to the web. We focus on providing prefix search over these fragmented datasets, so we want to make it possible for the client to find entities matching a specific prefix. We aim for an acceptable user-perceived performance, so the goal is that this can be used by applications on the web without significant slowdown compared to traditional server-sided solutions. We want to enable clients to take control of the query evaluation process. Now, to provide this functionality, what do we need? We need a dataset index. We need to be able to index the entities in our dataset to group them by the prefix values for specific properties. We require a self-describing fragmentation, so the fragmentation we create has to be traversable by the client, no matter how exactly the server decides to make this fragmentation. And we require a generic client that can, based on this self-describing fragmentation, can find results for the client query. So we will take a look at the first point, the dataset index. So to create a dataset index, we first have to decide what properties of the data we want to index. For example, here we have a person named Ruben de Dekker with an address. He lives somewhere in Ghent in the Albertlaan. Now, if you want to search for this data, there is multiple options. You might want to search for the person's name. You might want to search for the municipality, for the street name. So the first decision is what properties do we want to index, and do we want to provide prefix search functionality over to the clients. So what work do we want to do? And another question is what data structure do we want to use to index these properties? We've chosen balanced search trees and more specifically B trees as the main data structure to create our index. Why? These data structures have a maximum depth that can be calculated on beforehand, and this scales logarithmically with the amount of child nodes that is set per that a node in the tree structure can have. Next to the maximum depth, once we retrieve, for example, an entity in the node G, a subsequent query that results in an entity in the node E can make use of the already retrieved and cached fragments D and F to find their way in the tree structure to the data entities that they are looking for. So we can make use of the caching that these tree structures provide, and also the data locality, because if you make a typo, for example, and you go back a letter and add another one, these results will be very close inside this tree structure, and this will so you can reuse a lot of the data that you already retrieved, and you have less work to do for this new query. And you can already start streaming results. For example, there might be some results in the root node, there might be some results in the intermediary node F, and these results can already be shown to the client, so you can have a faster turnaround of results, and this will also show the client that there's actually something happening. So now that we have decided on which properties of the entities of the dataset that we want to create our index for our fragmentation, and now that we have decided on an indexing data structure, it is time to actually use this indexing data structure to fragment our dataset in a self-describing way, so that independently on which properties you create a fragmentation, or how exactly you create a fragmentation, that the client can still traverse the created fragmentation and find the fragments with the results for their prefix query. So the first thing we do is we create a dataset object, and we define the entities of this dataset as members on this dataset object. So you see, if we keep adding people to this dataset, eventually it will become so large that it is unusable to use in applications, as you first have to retrieve the whole data set. You have to process it locally, and in this time the user has to wait. So this is not this does not create good applications. So we want to use the indexing data structure that we have created to fragment this data set. So the first thing we have to do is we have to be able to define the relations and the terms in our indexing data structure. As we make use of balanced search trees for this, we require terms that allow us to define these relations and the necessary terms. And for this we have created our own ontology. And using this ontology, we define the fragmentations that we create for a data set as views on this object. So in this case, we see that we have a fragmentation of this data set available at /fragments /root, and this points to the root node of fragmentation of this data set. So now that we take a look in this root node, we see that all the members in this fragment of this root node, they are still defined as members of the original collection. So if you look for members of the collection, and while you traverse the fragments, you will always find all the data entities of the original collection that are stored in this fragment. And next to this, we of course need the relations between the nodes of the tree structure to be able to know which relations to which child nodes we have to follow at each step. So here we give, in this listing, we give an example of such a relation. So here we see that this relation leads to a fragment containing the entities of the dataset with a first name property that is greater than Alice. So if this matches what we are looking for, then we can dereference this node property and continue from there. So this way we can describe the relations between the different node fragments of the fragmentation. So now that we have had a quick look at how we can describe such self-describing fragmentation, we will need a client that is able to traverse such the fragments of such a fragmentation and can evaluate their prefix queries over such fragmentation. So to do this, for example, if we look for an entity with the first name property that matches the prefix of Carol, we first retrieve the collection object, and in this collection object we see that there are two fragmentations available and there are two root node linked. So we start out by of course discovering these fragmentations that are available, and we add these to a queue. Then we repeat while the queue is not empty. We take the first node and then we retrieve the corresponding fragment from the web. In this retrieved fragment, we check on the member property if there are entities of the dataset that are defined in this node, and if there are entities defined in this fragment, then we can return them to the if they match the user query. So, for example, if this fragment contained entities that match the prefix Carol for their first name property, we can return this to the user. And then after checking all the members, we check the available relations in this node to possible child nodes, and we check if these relations can lead us to more results for our query. So in this case, we again have the greater than relation for the first name property of with a value of Alice. So as we are looking for entities with the first name of Carol, we can see this is indeed greater than the value Alice. So we can now add the node that is pointed to by this relation to our queue, and we can continue the process. Okay, so now that we have explained our approach at indexing and fragmenting the dataset, it's time to evaluate the approach. So how good does evaluating prefix queries over these fragmentations actually work? And for this, we made use of two data sets. We made use of a data set of the transport stops, the public transport stops in Flanders. This one had 73,000 entities and containing in total 438,000 triples. And for this one, we had a query log available. Then we also made a fragmentation for the OSM names data set. This dataset has a total of 3.8 million entities and a total of 125 million triples. So this one has more, on average, more triples per entity in the dataset. And for this one, we did not have a query log available, so we made a randomized query log to evaluate this our approach over this dataset. Next, prefix queries. They are often not individual queries. They are often a series of letters that are typed to get to a certain word. For example, if we look for a street name, this will often result in a series of subsequent prefix queries, which are all tied closely together. And for this reason, we do this evaluation mainly on series of prefix autocompletion queries instead of just individual queries. So the first experiment that we did was look at the server cache hit rate. We did this over the transport stops data set, as we had a real-world query log available for this one. So we made a baseline query server API with a cache size that was 10% of the original data set, and we also hosted our own fragmentation on the server with a cache that was 10% the size of the original data set. And when we compared the results, we saw that the query server approach stagnated at around 20%, a server cache hit ratio of about 20%, so 1 in 5 requests could be served from cache. While we see that our approach took a bit longer to get to stable position, but eventually we could serve up to 50% of the requests for fragments from the server cache instead of having to search for the files. This can be explained by multiple reasons. For example, if the longest match in the dataset has been found, and any subsequent queries for entities that do not exist, or any queries for entities that start with a number, for example, that does not exist in the dataset, then these queries will also not have the client fetch new results. While in a query server approach, every prefix is queried to the server. So this, and also the use tree structure, which leads to a lot of reuse of the nodes higher up, closer to the root. This leads us to have a better cache hit ratio on the server. Next, we did an analysis of the efficiency of our approach. So with this we mean from all the results that we retrieve for a series of queries, how many of the retrieved entities are actually a result for our queries. And we saw that for a series of prefix queries that a large percentage of the queries, up to above 30%, had a very low efficiency ratio. But the other queries had an average of about a 50 to 60% efficiency ratio. So how can we explain this large amount of very bad performing queries for this use case? For this evaluation, we can explain this by, for example, if you search for a term that is not in the data set, then all the retrieved data all the data that is retrieved while searching for this prefix will result into a zero efficiency. Also, if you copy and paste a specific address in the search bar, which does happen in these real-world query logs, then the client will have to traverse the whole tree structure to find a single matching entity. So all the rest of these retrieved results will not will not count for the efficiency. So this can explain a large portion of the very bad performing query series. But if we leave those queries aside, we see that we can get to an acceptable 50% efficiency ratio using our approach. Then if we take a look at the bandwidth usage, we see that on a cold client cache, on average there between 10 to 15 kilobytes of bandwidth required to find the results for a series of prefix queries, and in the worst case we can go up to 25 kilobytes required for one series of prefix queries. So this is rather high. But when we take a look at when the client cache has warmed up, we see that the amount of required HTTP requests on the right is much lower compared to when having a cold client cache. And we see that this is of course translated in the bandwidth requirement for evaluating the prefix queries. And this can also be explained partly by the nature of the transport stops query. So if you query for transport stops, you will oftentimes look for the stop close to your home, for example, to see bus hours. And as you repeat the same query a lot, this will lead to a lot of hits in the client cache if these fragments are kept in the client. And this will lead to a very low bandwidth required. Now, when we take a look at the amount of results that are retrieved when evaluating a series of prefix queries, we take in this analysis we take a look at the first 3 queries in the series to have a good overview of how the process actually starts. When we take a look at this analysis of for the transport stops dataset, we see that immediately we have a jump from up to 5 results, and these results are the results that are cached from previous queries. And then we see that we have a slower start for the first query in the series, as this one has to, as not all queries start, but exactly the first letter. The client has to sometimes search for the position in the tree corresponding with this first query. So this first one can take a while. To produce results, and we see that we can get on average 13 to 14 results in an execution time of 150 milliseconds. But then we see that the second query in the series and the third query in the series can, as they already have found their starting position in the tree, they can much quicker retrieve the additional results required for the subsequent queries in the series. So we see a slower startup for the first query, but then a second and third query can make more speed. And then if we take a look at the larger OSM names dataset, we see a very slow start for the first query in the series. As this dataset is a lot bigger, the fragments, the entities also have more triples per entity, so the fragments on average are also a lot bigger, and we see that in this case the first query can struggle to even produce 10 results in the execution time of 150 milliseconds. This is also the case because these queries on the OSM names dataset are randomized and not real world, and these do not always start from the first letter. They are randomized to start at a certain position, a random position inside in the word. So the first query can have to search for the position in the tree where the results are stored for that first query. But then once we add another letter to this, we are already at a position where we can retrieve some immediate results and can quicker find some additional results. So we see this translated in the second and third query, producing a lot more results in the 150 millisecond execution time. So we see here again for larger data sets that the startup query might have some difficulties with producing 10 results, but then the second and third and other queries in the series can much quicker provide the client with the required results. when we finally we made an analysis of the fragment sizes. So with the fragment size of 25, we mean that a fragment contains 25 data entities as well as relations to 25 child nodes. So we tested this for fragment sizes of 25, 50, 75 and 100. And we found that for the smaller transport stops dataset, on average a larger fragment size led to a faster retrieval of the results. This is attributed to the fact that the depth of the tree structure is smaller, and that there is more results per fragment that is retrieved from the server, so it can give more results at a quicker pace, and it does not have to traverse that deep in the tree structure to find these results. However, if we compare this result to an evaluation over a much larger dataset with 3.8 million entities and with a deeper tree structure, we see the opposite, that the larger fragment sizes have trouble keeping up with user typing at 150 millisecond intervals. This is because the randomized query log makes it so that the first query has to search for the position in the tree where the results are stored, and then we see as we have a smaller fragment size, the fragments are faster to retrieve, faster to process, and so the client can traverse deeper into the tree structure at a faster rate than when using larger fragment sizes. And we see this result clearly in these visualizations. And for this, we chose a fragment size of 25 for all our other evaluations that we have done, because once we get into larger data sets, the larger fragment sizes can become less responsive, and they also require more processing from the client to retrieve and process the files. So here we have an example that we made for the dataset of the address registries in Flanders, and we can see we provided fragmentations over the municipality. We provided a fragmentation, and we provided fragmentation over the street names of Flanders, and we can see that as the user is typing, the client will retrieve more and more results that match the user prefix, and so for an acceptable typing speed, the client can keep up with the typing to provide the results to the user. So, did we succeed in what we set out to do? Well, we managed to provide a file-based approach to fragment the dataset that we can use to publish these fragments over the web with static solutions such as GitHub Pages. So we can publish these fragments as files over the web. These fragments enable clients to evaluate prefix queries over these fragments as they are self-describing. And this prefix evaluation gives acceptable user-perceived performance, as we have shown with our small demonstration and with the evaluations that we did. And we do give the client full control over this query evaluation process, as the whole evaluation of the query happens on the client side. Where do we go from here? We can expand to other areas, such as geographical data that we can index using R trees and explore with the same approach. If we can use our approach there, we can explore additional functionality for our approach, such as fuzzy string matching, and we also explore the publishing of live data using this approach, and this is done by my colleague also at ICWE 2021 in the talk Publishing Base Registries as Linked Data Event Streams. Here we have a small demonstration in the web slides where you can query 4 datasets simultaneously using our approach, and you can see the results for yourself if you want to try it. And if you want to make your if you want to have applications use your data, make it attractive to reuse, provide attractive fragmentations that can be used by clients and reusers to build applications over. For more information and further developments on this research, come find us at tree.linkdatafragments.org or send me an email at ruben.dedekker@ugent.be. Thanks a lot for your attention and have a great conference.